In the last lecture, we started chapter 6. Basically, what we did was to introduce momentum. We said that what is momentum? And I hope you remember them. What is momentum? Someone asks you, the answer is mass into velocity, right? Simple. So momentum is also a vector. Because velocity is a vector, momentum is also a vector. Then what we did was to introduce impulse. If we have a force, and depending on how long that force is acting on the object, we can define something called impulse, which is force multiplied by the time duration of that force on a certain object. So impulse is that. The symbol for impulse is capital I. So if you want to just remember the formula, it will be force into delta t, F into delta t is the impulse. Then we said these two are related. The impulse, which we define, and the momentum, which we define, they are related by what is called momentum impulse theorem. I is equal to delta p. So the more change will occur in the momentum. So I impulse equals to change in the momentum. Then we looked at the isolated system. In isolated system, we have conservation of momentum. We even solved questions where we apply the conservation of momentum principle. Okay. Right. I hope I did not close it. Yeah, it's minimized. Okay. Right. Now we go to collisions. You know what collisions are, right? When two objects hit each other, that is called collisions. So road accidents, that can be taken as a collision. So collisions, in general, everyday collisions meet these two criteria. They are very short in duration. Could you please quiet, please? So it happens in like milliseconds duration, okay, fraction of a second. So it's a very brief period of time. So that means the internal forces are important. The internal forces, when they hit each other, is a very huge force, like 100,000, 200,000 force. So during that brief period of collisions, we can ignore the external forces, like the gravitational force, friction, and the normal force. Those things can be ignored. So effectively, we can say during the period of collision, all the collisions happens in an isolated system. If we consider only that in the brief period of time, we can ignore the external forces, which are very small compared to the internal forces. So internal forces cannot change the total momentum. They can change individual momentum, but the total momentum will be conserved if we consider only that brief period of collision. So if we say, calculate the total momentum right before the collision and calculate the total momentum right after the collision, and they should be equal. So external forces are therefore negligible during the collision. So we can say total momentum of colliding objects remains almost unchanged. So in general, I will say total momentum is conserved in any collision. So because of the collision, there will be no change in the total momentum. It will only redistribute among the objects, but the total momentum right before the collision will be equal to total momentum right after the collision. So collisions are two types. One is called elastic collision, and when they are not elastic collision, we call it inelastic collisions. All collisions are of two types: elastic collisions and inelastic collisions. So how do we distinguish between them? By looking at the kinetic energy. Because momentum is conserved in both of them. Elastic collision, we said in the beginning, in any collision, momentum is conserved. So whether it is elastic or inelastic, momentum is conserved. What distinguishes them is the kinetic energy. In elastic collisions, kinetic energy is conserved. So like we have the momentum is conserved, kinetic energy before collision will be equal to the total kinetic energy after collision. Then we call those collisions as elastic collision. When that doesn't happen, if the kinetic, in general, it doesn't happen. In general, most of the collisions are inelastic. They're not going to be conserved. So most of the collisions are inelastic, and certain collision, when the kinetic energy is also conserved, we call it as elastic collision. Within the inelastic collision, where the kinetic energy is not conserved, we have a special case, a subclass, which is called perfectly inelastic collision. It is inelastic collision, but something special happens when these objects collide. They stick together, bind together, or glue together. Then we call those kind of collision, yes, it is inelastic, but we have an additional qualification. We call it perfectly inelastic. So whenever you see a collision where they combine, stick together, we know for sure it is inelastic. And we also have a special name for that. We'll call it perfectly inelastic collision. So we can sketch these collision by drawing diagram. Let's say there are two objects, M1 and M2. We'll start with this perfectly inelastic collision because they are easy to deal with. When they combine, you know what happened? After the collision, they become just one object. In other words, both of them will have the same final velocity, right? So suppose the blue ball, the mass is M1, and the orange ball, say the mass is M2. Before collision, M1 has a velocity, so 1 for the ball 1, initial for the before collision, we will say this is V1I. This is the notation we are going to use. M1, V1I, initial velocity of 1, so V1I, the sub 1I. So M2, initial velocity of the number 2, and I for before, or initial. And they are moving such that it's one-dimensional. When they hit each other, after hitting also, they will keep the same straight line, x-axis only. It may reverse the direction in the opposite direction, but it will not escape from the x-axis. So it's a one-dimensional collision, head-on collision we call it, one-dimensional collision. So M1, M2, V1I, V2I. When they combine, they're both going to have the same velocity because they are moving together. So we don't need to have V1F and V2F, we will have just a V. So that is perfectly elastic collision. So I have a feeling I missed something. No, okay, right. I didn't miss any. I didn't skip any slide. It's fine. So we begin with the perfectly inelastic collision because it is easy to deal because after collision there is only one velocity. And suppose I know the masses, I'll ask anyone talking to leave. I'm talking, you're also whispering, so that is, you're not listening to me, please. So M1V1I plus M2V2I is the total momentum before collision. I can put it like this. So suppose there are two objects, sum of P1 plus P2. So this is the total momentum before collision, equal to total momentum after the collision. That is conservation of momentum. Although it's an inelastic collision, I can apply the conservation of momentum. So the sum of the momentum will be momentum 1, which is M1V1I. The momentum of the second one, it will be M2V2I. So sum them, that will be the total momentum before. Afterwards, we have only one object. We can consider them as one object. They glue together and they have only one velocity. So I can take both of them together as one mass, M1 plus M2, and we have the velocity as V final. So this is the conservation of momentum expressed mathematically. So we will be answering question using this equation. Only thing we have to worry about here, it's a one-dimensional, but it's a vector equation. So if we have a positive direction and the velocity is in the positive direction, you will substitute the velocities as positive. Suppose it's in a negative direction, you will make sure that you substitute with the negative sign. You need to take care of that. So that's what is being said here in this slide. Momentum is a vector quantity. Direction is important. Although it is only one-dimensional, still we have a positive direction and a negative direction. So positive direction, you must substitute positive value. Negative direction, you have to put the negative sign. Right. Elastic collision, that was a perfectly inelastic collision. Elastic collision, we will have two velocities after collision. It is not the same. This is the conservation of momentum equation. This is the total momentum before collision. And this is the total momentum after collision. So we have m1 v1f, that is the final velocity of mass 1. v2f is the final velocity just after collision velocity of m2. In addition to the conservation of momentum, I can write the conservation of energy also. Now this one is the equation for conservation of energy. So what is on the left-hand side? The sum of all the kinetic energy initially is equal to, this is the sum of all the kinetic energy finally. So you know the equation for kinetic energy is half mv squared. So this is the kinetic energy of the first object before collision, half m1 v1i squared. This is the kinetic energy of the second object, half m2 v2i squared, equals to, after the collision, kinetic energies. Now, suppose the masses are given and the initial velocity are also given, we are going to end up with the equation having two unknowns. The final velocity of 1 and final velocity of number 2. And it occurs in this equation as well. We can find both of these v1f and v2f because we have got two equations with two unknowns. We can solve them simultaneously, okay? A set of equations for two unknowns, two equations. And there are methods to solve it, rather than doing all the algebra, by eliminating one unknown from equation 1 and putting it in this, and then finally we have an equation with only one known and we solve for it by elimination method. We will not go into all those things. We'll just use our calculator to solve it, and I will show you how to do that. And we'll also have an easy method because we don't want to deal with this equation, which is if these are the unknown v1f and v2f, it comes with the square term. Then it becomes a bit difficult to solve. So what we do, we take these two equations, combine them, and arrive at a new equation. This is the guy. And this equation is a vector equation, unlike this. This is a scalar equation, okay? Remember that. These are speed. This is not velocity. But the conservation of momentum is a vector equation. Conservation of kinetic energy is a scalar equation. So we combine this. If I call this equation number 1 and this as equation number 2, I produce another equation. Let me call it equation number 2 dash, which is a combination of 1 and 2 previously. So this has both conservation of momentum in it, also the conservation of kinetic energy in it. You don't have to worry how I got it, okay? It's involved little bit of math. You don't need to worry how to prove it, but just know this. So I will take this as my equation number 1. This is the conservation of momentum. And this guy as my second independent equation, the conservation of energy. So in place of the original conservation of energy equation, I have got another vector equation, which has both the conservation of momentum and the conservation of kinetic energy in it. So now I will forget about that conservation of energy equation. I will use these two equations to solve problem. The first one is conservation of momentum. The second one as the conservation of kinetic energy equation. So I'll take example and I'll show you how to do that. You need to know what these symbols mean. You know what is V1I and what is V2I. Do you have to memorize it? Not really, but just try. Remember, I will say try to remember it. So that means you don't worry about forgetting it, because this equation will come in the formula sheet. In the second equation, you don't see the mass, right? That's the beauty of that equation. So it applies to whatever the mass here. The question needs the V on. The second one. Yeah, right. Yeah. Suppose, because the second one doesn't have the mass at all. Suppose they are given you V1I and V2I and say V1F, you don't even need this equation. But this equation, if you want to apply both of them, that collision must be an elastic collision. All right. If it is not an elastic collision, you cannot apply number 2. Number 2 is only for elastic collision. Number 1 is for all collisions. Right. Let me summarize. So the collisions are 2 types: elastic collision and inelastic collision. In elastic collision, both momentum and kinetic energy are conserved. In an inelastic collision, it is not so. Only momentum is conserved. Kinetic energy is not conserved. And within the inelastic collision, we have a class called perfectly inelastic collision. How do I know something's perfectly inelastic? If they combine, so stick together or bind together, then we know it is a perfectly inelastic collision. Now, sometimes, you have this idea in your mind. Elastic mean they bounce. No, that is not correct. Elastic mean kinetic energy, total kinetic energy before is equal to total kinetic after. That is the only thing. Just because they bounce back doesn't mean elastic. They may be elastic or may be inelastic. We no guarantee. Okay. So this is one of the something in your mind that is very difficult to get it up, because already absorbed into you. So you don't make that mistake. Okay. Just because they bounce doesn't mean they are elastic collision. They may be elastic or may not be elastic. Okay, right. Can you say for sure it is inelastic? No. Can you say sure it is elastic? No. Answer is no for both questions. Right. But if they combine, it is inelastic. It's not only inelastic, it is perfectly inelastic. Okay. Right. I hope I made that clear. If they combine, right, after collision, they become one object, stick together, we know for sure it is inelastic. That is the only place where you can be certain that is which category it falls into. We know it is inelastic collision. Additionally, we have a special name. We call it perfectly inelastic. Right. So now, when you have a problem, you sketch a figure, right? This is for when they don't, it's not a perfectly inelastic collision. In general, we have, say, a blue ball, which is mass m1, and the second one m2. So you will say the velocity is v1I for the blue, the first ball, the second ball v2I. Then we will draw another picture after collision. The v1I is not anymore v1I, it will change to v2I. And V1F, V1I will change to V1F, and the V2I will change to V2F after the collision. So you need to draw a picture like that before you start solving questions. Now, when they are perfectly inelastic, then what happens? M1 and M2 become just one object. There is no need for V1F and V2F. We drop the the 1 and 2, we just call it Vf, because that is become unnecessary, right? We have only one velocity anyway after collision. So now we are ready to do a question. So this question, we have a day-to-day collision problem, like 2 vehicles. So we will call one of the vehicles, say the truck, as M1. I don't know why, okay, M1. And its velocity as v1I. And the car, we will call it m2, and its velocity will be v2I. And after collision, we have just one object with the velocity mass of m1 plus m2 and the velocity vf. So can I apply conservation of momentum? Yes. Any collision you can apply conservation of momentum. So this is valid. Let's see what is given to us. M1 is given. Okay, the pickup truck, M1 is given. And V1I is given, the velocity of the pickup truck. M2 is given. And V2I is given. Okay, right. M1 given, initial velocities are given. Masses are given, initial velocities are given. He is asking A, find the final velocity of the combined object. The answer is there. Let's get the answer ourselves. So only equation we need is only equation we can apply is the conservation of momentum. Can I apply the conservation of kinetic energy? No, it's an inelastic collision. So let's apply. M1, you put 1100. V1I, it's a vector equation. Always remember, it's why it is in bold. It's a vector equation. So we have to put the correct sign. So right side we take as the positive, which a pickup truck is going. So I will put positive 15. And M2 is 900, V2I, because it is coming in the opposite direction, so negative 15. And then this, and this is the unknown. So you can just do simple math and simple algebra, make the V1, Vf as the subject. You can do a calculation, but you can just put everything in the calculator from the beginning, and you can get the calculator to solve for it. That's also okay, right? So always please use the calculator in the solving mode. Practice that, don't do it only just before the exam. You should be confident you know how to use the calculator in the solving mode. Then you will not make mistake. It will save you time. In exam, it is very important, right, to do the question as fast as possible because there's a time limit. Right, then the question B is, find the change in the velocity of each vehicle. We have two vehicles, right, M1 and M2. Initial velocity of the truck is given plus 15. So it's going to the right. Final velocity we just found plus 5, right? It's also in the plus 5. So the change in the velocity will be final velocity minus, these are vectors, right? Even that, okay. Velocity, we didn't say the speed. So plus 5 is the final velocity minus plus 15 is the initial velocity for the truck. So you get the answer to be negative 10. So there's a change to the left, right? So negative value, the change in the velocity is to the left. You know that. Because why is it left? Because final velocity is still to the right, but it has reduced. So the change is to the left. Okay. What about the car? Final car's velocity minus the initial car's velocity. Final car's velocity is 5, same as the final velocity of the truck, minus the initial car's velocity is to the left, minus. So minus will be plus. So the total change for the car is plus 20. So what it means, the car is initially going to the left, but its velocity is completely changed to the right. Okay, so that's why delta V for the car is a positive value. Okay, and then the C is a kinetic energy change. I didn't do that, but you know how to do that. The expression is there, matter of substituting. Now let's do another collision question. It's also from one of the past exam question. Okay, so here, sometime the physics the physics is to apply to the conservation of momentum principle. You know the physics, even if you forgot it, it's in the formula sheet. But if you can't understand the question, then it's a problem. So sometimes understanding the problem is 90% of doing the problem, because Formula sheet is there. You understand about collision. So you know any collision momentum is conserved. That means you know which equation to apply. But here the challenge is whether you understand the problem or not. Okay. Reading, comprehension. So let's read it. There is a ball, bowling ball. So let me take that as my number 1. So M1 is equal to 7 kilogram. And it strikes a 2 kilogram pin. So that may be the second object. So let me say this is the M2. Good. The pin, which is the M2, flies forward with a velocity of 6.0 meter per second. So it is what? It is V2F, right? Not I, V2F. So that is the challenge here. Do you recognize them for what it is? This is V2F. The pin is the number 2, and the pin having a velocity after the collision. So that is really V2F. And the ball, it is the M1. Now we are talking about the number 1. After it is having a velocity, this is V1F. So we know the M1, M2. We know V1I. We know V2, V1F and V2F. So yeah, we know this, we know this, we know this, we know this. We know this. We V1I, we don't. V1I, we don't know. Okay, it is not given. V2I, yeah. Right. So you understood the question. So this bowling ball is, you know the game, right? The bowling game. You throw the ball and there are pins. Pins are, you know the common general knowledge. Pins are at rest before. So that means this is not visible, explicit in the question. You don't see that it is so. But it's a general knowledge. So you know this is equal to 0. The pins are initially at rest. So this we know, this we know. This is given, this is given. The only unknown is V1I. So just put it in the equation. Take your calculator, write the equation, call it X. Write it in your calculator and ask the calculator to solve for X. We have the answer, done. Right, and this one, it's a little challenging because now we have, they don't combine. And also the previous one also they don't combine. But if there is only one unknown in that question. There was only one unknown in this question. And let me go back to this question. Do we know it is elastic collision? Yeah, because it's not elastic. I told you. Yes. Unless the question tells you it is elastic, you cannot assume. Okay? We don't know whether it is elastic or inelastic. So we can only apply the conservation of momentum. I cannot bring the conservation of energy equation. But there's no need. I can solve the question with one equation because the question gives all the things except one unknown. So one equation is enough for us to solve. So just solve it. If someone asks you, is this an elastic collision? Your answer is, I don't know, because he didn't tell me. There's no way of knowing. But we can check. If we can now calculate the kinetic energy before total, kinetic energy after total, and if they are equal, then we can say with confidence it is an elastic collision. But that is not part of the question, so we ignore that. Right, now let's do this question. This question is, there is a ball, 2 kilograms. So let me call it number 1. So it is M1. Moving with the speed of 3 meters per second due east. So let me take the east as my positive direction, so it will be plus. So this is V1I. Good. Make a head-on. Okay. The meaning of head-on mean they are going to, no. Head-on mean they will be in the same axis. One-dimensional. It is guaranteed. He will say, is you hit like that, then after collision also they are going to move in the same axis, same x-axis. They will not go like that. They will not change direction. It will be either in the same direction or in the opposite direction. There's a possibility to reverse the direction, but that's the meaning of head-on. Head-on, also it is given here, right? one-dimensional. Elastic, he's saying it is elastic as well. Then I can take both equation. Not only conservation of momentum, I can bring in the conservation of kinetic energy as well. The second equation can also be used. Right, then keep going. Another mass of 3 kilograms. So this is the M2. And speed of 5 meters per second due west. So this is V2I. It should be a negative. Why? Because you have chosen east as my positive direction. West east is my line. Okay, either you have to go to east or to the west. There's no other choice. It's a one-dimensional. And since it is west, I put negative. It is not there because he's telling us the speed. Speed means magnitude, right? So what I need is velocity. So the velocity will be minus 5 meters per second because it is in the west direction. What is the final velocity of the ball after collision? So he is asking for what is V1F and what is V2F. So we'll take the conservation of momentum. This is the equation that is in the formula sheet. Substitute. M1 is 2. V1I is plus 3. Okay. We know it is going to east. M2 is 3. And V2I is minus 5. Now, you know why it is minus, why I put the minus. It's not in the question, but he's saying it is west. It's in the opposite direction, so negative. Then M1 is 2. This is unknown. I cannot do anything. M2 is 3. This is also unknown. I have to leave as a symbol. We don't know what that value is. Yeah, yes. Let me simplify this as much as possible. This side, this is 15. Sorry, this is 6. This is 6, this is 15, 6 plus minus 15. So this is a plus here, right? So that will be whatever it is, that is minus 9. And 2V1F plus rearrange, bring it to the left side so you get this equation. Leave it there, I'm coming to that. Can I solve for V1 and V1F and V2F here? No, it's one equation but two unknowns. I cannot do anything. So I will keep it there. I don't lose hope. I know I can get another equation, which is the conservation of energy, but the simple form, the linear form. This one, okay? V1I minus V2I with a vector equation equal to, it's not difficult to remember. See, this is the difference, right? This is also the difference afterward, but with the negative sign. So that's how easy it is to remember it. I'm not telling you to memorize it, but just take an effort to remember. So that's why I'm saying remember. I don't say memorize, okay? Even if you forget it, no problem. You can look at the formula sheet and you know that. So let's substitute here. V1I is plus 3, subtract. V2I is minus 5. Then we goes in, it become minus V1F, minus minus become plus, and you get this. Then I can rearrange and write like this. Right. Now, how do I do this? Two equations with two unknowns. There's a standard method of doing it by eliminating one unknown and making it an equation with only one unknown. This is the math, okay? We have the calculator. So we will use the calculator to solve it. Let me bring the calculator now. This is the method, right? So you have one equation with two unknowns, another equation with the same two unknowns. And these unknowns have their coefficient. This is the equation. Say the equation number 1 will have A1x plus B1y equal to C1. You have to write it in this manner. So that is what I did here. 2 multiplied by x plus 3 multiplied by y is equal to C, which is minus 9. Okay. So this is A1 is 2, A2 is 3, and A1 is 2, B1 is 3, and C1 is negative 9. And from here, you get the second equation. This will be A2 is minus 1, B2 is plus 1, and C2 is plus 8. If you know your A1, B1, C1 for the first equation and the A2, B2, C2 for the second equation, the x and y are the unknowns. So in our case, x is V1I, V1F, and y is V2F. So you take your calculator. I have to get my calculator. Yeah. How do I get the calculator? Okay, here. Desktop. Okay, now I have the calculator. Let me go to the calculator. Yes, that's it. Let me clear this. I will get it back to the way you see the calculator. This is how you would see the calculator, the computing normal mode, right? You have to change the mode. Mode, when you press this mode button, it will bring all these modes. This is the normal computing mode. I need the equation mode, okay, to solve set of equations. So that is phye, right? So you press the button phye. And then you have different kinds of, the first one is the linear equations, okay, for two unknowns, a and x, b and x, c and. So press number 1, right? So you get this. Now you have like a matrix. Now you input your A, B, C, A1, B1, C1, and A2, B2, C2. So A is what? For us, 2, right? Okay. A1 is 2. Equal. It goes there. It goes to the matrix. B1 is what? 3. And enter. And C1 is what? Negative 9. Use this negative, okay? Negative 9, then put equal. You got the A1, B1, C1. Now time to put the A2, B2, C2. A2 is negative 1 equal. B2 is positive 1. Press the equal button, that goes in there. And the C2 is 8. Right, you got all the thing. Now you press the equal button. There's no shift calc, okay? You just press the, not like the equation solving. This is different, just equal. This is the x. X mean B1F. So probably you don't see, just make it decimal. You see that 6.6, negative 6.6. And then press the equal again, you get the y, which is the V2F. And again, if you want the decimals, you press the this button, where is that? SD 1.4. And that's it. Okay. So the whole algebra, you don't have to do it. You just use your calculator and it will solve the set of equation in this way. Mode 5 and 1. Yeah. Mode will bring all the choices. Then you go and look for the equation, which is number 5. So press the 5. Then you will have, within that you will choose the first one, which is for the linear equation, solving the linear for two unknowns. Right. Good. Let's go to the next. I will skip this. It is similar. Glancing collision. What is glancing collision? See, now you know you have played this snooker game. You know there's a disc, and you hit the other one. If you, let me say, I connect this line center to center. If you apply a force along the center to center, it is called the head-on collision. It will hit. After collision, they will move in the same axis. Maybe it will reverse. Maybe it will go in the same direction. But it will be moving the same x-axis. But suppose I apply the force at an angle. I don't apply the force along this line. I apply the force like this. Then it will move like this. And when it comes here, it will be hitting at an angle to this center to center line. This is called the glancing. You know what is glance mean? If you look at you like direct, it is head on. But I go like this and like, it is glancing, right? So, it is not direct thing. So if you hit at an angle, it is a glancing collision. And what happened after collision, these two balls will move in different direction. So it becomes a two-dimensional collision. So still I can apply the conservation of momentum. Only thing is I have to apply in the x direction. In the x is equal to total momentum after collision in the x axis. Then that is along the x axis. Then you will have another equation along the y axis. Total momentum finally in the y direction. So instead of one equation, now you will have two equations, but it doesn't help us. I mean, of course it helps. I mean, if you have only one equation, then but we got four unknowns, right? I mean, V1 fx, V2 fx, V1 fy, V2 fy. Okay, so we got, instead of 2 unknowns, we are now having 4 unknowns. But anyway, we got 2 equations. Suppose enough of them is given, if I can reduce to just 1 unknown, I can solve it. If it's an elastic collision, then we can also have the elastic equation, the conservation of kinetic energy equation. Then, but usually for glancing collision, 2-dimensional collision, we will not give you to use the conservation of kinetic energy as well. It will be too difficult. So we'll stop with, we'll give enough variables, so we'll end up with just 1 unknown. Here, an example of a glancing collision, but we make it a little bit easy by making the V2I at rest, the mass M2 at rest, 0. When you have a 0 in an equation, it will become simpler, right? And M1 has a velocity V1I, M2 has a velocity of 0. They hit it at a glancing angle, so blue ball and the green ball, they will deflect, so they will not move in the x-axis, so it's a 2-dimensional problem. So we can going to have to resolve the component. So this M1 will make an angle of theta. Let's say this will make an angle phi. So there are going to be 2 angles involved. So the blue ball x velocity will be V1f cosine theta, and the y velocity will be V1f sine theta. And similarly for the green ball, we will have V2f cosine phi and V2f sine phi. Then we can apply the conservation of momentum in the 2 direction. This is one example. I will skip that, but I will do this one. This is from a midterm question. Midterm questions are simpler compared to those homework problems. So let's see how we can do this. So we have here a 1,000-kilogram car, so let's call it M1. Here it is, you've been helped a lot, even the notation is given. So we are going to call this M1. Approaches the intersection. So let me draw the picture for this. Let me say this is the west-east. So this, let's say, south-north. So this car approaching an intersection of a road, and it is moving. Let me draw the car like this. M1 is moving toward east so this is M1. So this will be V1I is equal to 20 meter per second. So it being helped, because we are giving it as component form. So it is only in the east. So no east. Pay attention here, please. So the velocity is, x component is 20, no y component is 0. Another car, let me say this car, this is moving north, right? Another car approaches the same intersection traveling north, so it is going like that. So this is V1I, V2I is equal to no velocity in the east, so 0 x component, and plus 20 y component. It's not south, it is north. So I'm taking north as my positive. They come here, they hit each other. After collision, they become just one object. Because they entangle. The word is a lock together. You understand what? Sometimes you will see entangle. Same meaning. Glued. Stick. Vocabulary is also important. Okay, you should know what they mean. So you'll say lock together, that means they stick together, or entangle, glued, stick, they all mean the same thing. For us, they all mean the same thing. Then ignoring external forces, that means I can apply conservation of momentum to solve this problem. So they become one object and it has one velocity. We have to find this one velocity. So knowing how to deal with vectors, this question can be answered very easily. So let me make use of this space here. What is the equation? M1 V1I as a vector plus M2 V2I as a vector again equal to M1 plus M2 V final. Very easy. Only thing is you have to get them adding vector addition. You should have to be careful. So 1000 multiplied by V1I is 20 plus M2 is also 1000 vector is 0 and 20 equals M1 plus M2, which will be 2000 VF. Now it's a simple one actually. Now we did this in the Newton's second law. We did something similar. So I don't think I should continue. Please do it, okay, at home and get the answer. He is asking for what? What is the velocity? So you give it as x component, y component. If you say what is the magnitude of the velocity, Pythagoras theorem, x component square plus y component square, take the square root. I will stop now. Actually, I finished the whole chapter, so I can stop. Yeah, we finished chapter 6, yeah.